There's a certain profound irony in the fact that we'll ultimately learn that time is relative, and yet we'll start at precisely 5 minutes past the hour. Welcome back. Today we're going to go through Chapter 2 of our Relativity course. This is titled Perplexities in the Propagation of Light. In the last class we focused on matter, particles, but the world is made up of particles and radiation. And we're going to shift focus from particles to fields, from point particles and classical mechanics of point particles through to the classical mechanics of waves, and in particular classical electromagnetism, the theory underpinning the theory of light. Eventually, when we articulate the relativity principle, which will be in the next class, it'll be clear that the relativity is not some isolated area of physics. Rather, it's almost a meta theory in the sense that it touches all of physics. You know, ultimately, we'll say things such as all physical laws must obey the relativity principle, and so this statement makes it clear that relativity is, in some sense, special. Pardon the pun, in the sense that it touches all of physics. It must influence all of physics. This is true of special relativity, and is can also be generalised, of course, in general relativity. But today we're going to focus on some perplexities in the propagation of light. We're going to revisit that old chestnut, the question of the nature of light. Is it a particle? Is it a wave? From the perspective of late 19th century physics. A second thing is we're going to introduce the idea of an ether, or more precisely a luminiferous ether. This was a supposed medium that carries light. Detecting the motion of this ether relative to the Earth was the subject of the Somoli experiment and a later Somoli experiment, which gave a very profound result, the most profound and important null result in all physics. If time will introduce the idea of inertial reference frames. Again, I'll use the term relativity very, very little in today's class, but I promise you that we'll start introducing the term relativity with its full glory starting in the next class. So let's jump into Chapter 4, or Section 4. So, is light a particle or is it a wave? Now, the idea of light being a particle, or more precisely it being a ray, dates back at least as far back as Pythagoras, several centuries BC. And the particle or ray theory of light nicely accounts for several features of light. The idea of light rays travelling in straight lines, the related effects of the sharpness of shadows. Yep. So if you have some obstacle and you have some light rays travelling in straight lines and you have some detector D, then the intensity I versus position X will look black. I use this thick chalk so it doesn't do this. If you want to laugh, watch me use one of these little chalks once in a while. So you have the sharpness of shadows. Also, the idea of light as little bullets that travel through space also accounts for the fact that light can travel through vacuum. The classic example here is sunlight travelling through the near vacuum of interstellar space. Now we can counterpoint this older theory of light with a newer theory of light, moving forward to people such as Hooke and Huygens and Newton, who championed this wave theory of light. And wave theory of light, the culmination of which is the Maxwell equations of classical electromagnetism. We're restricting ourselves to classical theory here. The wave theory of light naturally accounts for several phenomena such as interference fringes, phenomena such as diffraction. Yep. That if you do this experiment here with laser light, for example, you don't get a sharp shadow. Instead, you get some diffraction fringes. Instead, you'll get some diffraction fringes like this. Yep. This is diffraction. So the wave theory of light nicely accounts for diffraction. By the way, if you take a wave theory of light, and you take the wavelength as quantified precisely in Maxwell equations, and the entire theory of classical optics can be derived from the Maxwell equations as a starting point. If you take the wavelength to naught, you'll get, as a so-called asymptotic limit, you will get light waves travelling in straight lines. You will get sharp shadows. If you take the limit of the wavelength tending to naught, this diffraction pattern will become the sharp step function. But the idea of light travelling through a vacuum is not readily explained by the wave theory. Again, we need to look at this from a 19th century perspective. Waves need something to wave in. You can hear me speak because there's air filling the room. If you suck all the air out of the room, you won't hear me speak, and then you'll all explode and make a big mess. But the point is, waves need a medium to travel through. Water waves travel through water, sound waves travel through air, seismic waves travel through the ground, compression waves travel along sticks. Light is a wave. It has this successful Maxwell equation that explains so much. Therefore, it must wave in something. Therefore, vacuum doesn't exist. So this is the logic that was used by 19th century physicists, and it's easy to laugh at now in the perspective of hindsight. But the point is, this was a very compelling argument. Wave theory, this modern wave theory, quantified in the Maxwell equations, works beautifully, explains all this stuff. Limit case gives geometric optics with your straight lines and your rays and your sharp shadows. But everybody knows that waves must travel through a medium. Therefore, vacuum doesn't exist. Therefore, it might appear to be a vacuum to us, but it must be filled with some medium. And this medium was known as a luminiferous ether. So luminiferous as in light ether. So it was considered as self-evident to 19th century physicists that this ether exists, this medium that carries light waves. And the search for this ether was considered one of the most urgent problems of 19th century physics. Now there's some quotes that I could read out from Maxwell and from Oliver Lodge, just making the point that the existence of this ether was considered as self-evident and obviously true. Now sure, now we can say E equals mc squared. If you have energy associated with light, there's mass associated with it, which sort of gives it a tangible existence, independent of it needing to wave in something. You can just have energy propagating through vacuum. What's your problem? But remember that this is preceding Einstein's results. Although there's a certain irony, the Maxwell equations are actually fully consistent with relativity. If you stare at the Maxwell equations hard enough, you'll actually see the relativity principle in action. Now, it took Einstein to see that, and we'll get to it in due course, but the point is, late 19th century physics, the ether obviously exists. Maxwell spoke of the vast interplanetary and interstellar regions no longer being regarded as waste places in the universe. We shall find them to be already full of this wonderful medium, this ether. Oliver Lodge, writing, by the way, in 1925, which was disgracefully late to be saying such things, made the analogy between a deep-sea fish hooning around in the ocean, doesn't really think of water as a medium that surrounds it. For a deep-sea fish, water is its vacuum. Water is what you have when there's nothing else there. So the deep-sea fish swimming around would be oblivious to the fact that it's immersed in water, just like we're oblivious to the fact that we're immersed in the ether. But there are some things that are a bit difficult to swallow, that if I take some rigid piece of matter and I bang one end, I'll get waves that go through it. And if I could be a bit loose, the more rigid this material is, the faster the waves travel. Well, light travels really fast, therefore the ether must be really rigid. But I can wave the stick around and there's this ether, and the underlying ether in which we're immersed like deep sea fish in water, there's no resistance opposing to it. So there's this really, really dense, really, really rigid medium, and yet it's sufficiently tenuous to allow matter to move through it without any appreciable drag. So it seems almost self-contradictory. But again, the existence of this ether was considered to be the medium that carries light waves. What are light waves? They're ripples in the ether. Question, how can you detect this ether directly? And this leads us into the Somoli experiment. But before I mention that, I want to mention a consequence, an important consequence of the ether theory of light. And by the way, the Maxwell equations were developed in the context of an ether theory of light. Again, there's a certain irony there. So I want to explore one consequence, and I will use the word relativity in a second, or relative in a second, a consequence of the ether theory. Light waves are waves in ether. Water waves are waves in water. If this is a lake that I'm looking at from above, and I throw a rock in to the lake, it will send out water waves as a ripple. And the speed of those water waves is independent of the motion of the source. Whatever velocity I throw the rock at into the water is irrelevant. The speed of the water waves in water has a precise meaning. It's the speed of those wave crests relative to the stationary water, or relative to a frame of reference in which the water is stationary. So a person sitting on the ground here with their XYZ axis and their clock, and when they throw the rock in, the speed of water waves, which is defined as the speed of the water waves relative to a frame of rest in which the water is at rest, the speed of the water waves is independent of the motion of the source. So too with the ether. The idea of the speed of light is unequivocal. It's the speed of light relative to the ether, or more precisely the speed of light relative to a frame of reference in which the ether is at rest. Maybe the whole ether is moving at constant velocity through space. Maybe the ether is turbulent, but at any point in space, go to a frame of reference in which the ether is at rest. That is the speed of light relative to the stationary ether. Consequence of ether theory, of a medium-based wave theory, is that A, the speed of the disturbance is independent of the motion of the source. Point 2, if you're in a boat, you're a physicist B in a boat who's moving at some velocity v, then the speed of the water waves will be relative to the motion of the observer. So point 1, the speed of the waves is the speed of waves relative to the absolute frame of rest, which is stationary water or the stationary ether. Point 2, the speed of the waves is independent of the motion of the source. Point number 3, the speed of the waves is dependent on the motion of the receiver. Excellent. So this is going to be a prediction of the ether theory. And some of those statements will be right, and some of those statements will be wrong. But the question is, here we are in the Earth. The universe, the cosmos, is filled with this ether, and we don't know what this ether is doing. Even if the Earth was stationary relative to the ether at some point in time, it's going around the sun. And so if it was stationary relative to the ether at some point in the seasons, it would be moving relative to the Earth, relative to the ether at some later point, unless it mysteriously dragged the ether along. So we should expect some so-called ether wind, some motion of the ether relative to the Earth. Question, how do you detect this? Answer, you do the Michelson experiment, 1881. Or then you do a better experiment later, which is called the Somoli experiment from 1887. So this is an experiment expressly designed to detect the motion of the ether relative to the Earth, to detect this ether wind. Again, from the argument I've just given, you would expect the motion of the ether wind, the velocity of the ether wind, or the magnitude of the velocity of the ether wind, to be greater than or equal to the speed of the Earth relative to the Sun at least some point during the season. And by the way, the speed of the Earth relative to the Sun is roughly 1/10,000th of the speed of light. All right. So how do you detect the ether wind? Answer, Somoli experiment. So this works as follows. You have some source of light S, and this is 19th century, there's no lasers, but this light is as close to monochromatic as one can reasonably make it. This light from a source S then passes through a partially silvered mirror P. Partially silvered mirrors transmit some light and reflect some light. So when you pass through the partially transmitted mirror, there'll be one beam that passes through. It's then reflected from a mirror M, comes back again, some of which will be reflected down, and then there's some telescope T down which you can look. Yep. So this is a telescope T down which you can look. So this is one path of the Michelson interferometer. It's an interferometer because we're going to have two beams. Another beam is partially reflected from the partially silvered mirror, reflected back from a second mirror M2, some of which transmits down and again is detected by the telescope. These are spoken of as two arms of the interferometer. These two beams are being combined. So what you will see here will be interference fringes. So a typical image here would be to see some interference fringes resulting from the interference of these two light beams. Now we want to immerse this thing in this ether wind. Yep. Now for simplicity, 98% of relativity books consider the simple case where the ether wind is travelling at some velocity v which happens to be parallel to one of the arms of the interferometer. If you want to drop that assumption, do exercise 9, which is horrendous. All right, so we're going to have this assumption that the velocity travels parallel to one of the arms. It's an assumption which is easily dropped in principle. The results here can be generalised. You'll get the same result in the end, which is that the ether doesn't exist, but you'll have several pages of algebra to do so. I refer you to exercise 9 if you don't want V to be parallel to one of the arms. By the way, I've got a sneaking suspicion that my complex calculation of arbitrary V can be simplified, and I'm thinking of asking you to do that in an assignment. We'll see. So we have the Michelson interferometer, we have our ether wind, and the claim is that these fringes will move in position. These interference fringes, these interference bands will move in position, and as the Earth goes around the Sun, you would expect the ether wind to change velocity, and so you would expect these interference bands to move from season to season. Alternatively, if we take this whole apparatus and rotate it, for example, through some angle, you would expect these fringes to move as a result of the ether wind. That's a key point we want to calculate. How much do these interference bands move when you rotate the interferometer? We're going to choose 90 degrees anti-clockwise. How much do these interference fringes move between one configuration and the next because of the presence of this ether wind? Because what is the speed of light? The speed of light is the speed of light relative to the medium. What is the speed of light here? Well, the speed of light c is relative to the ether, but here light's going this way, the ether's going that way. So the speed of light in this piece of the first arm will be c minus v. The speed of light in a return trip will be c plus v. You might need to do some Pythagoras' theorem to work out the speed on these two arms. I'm going to leave that to an exercise. The point is that the speed of light relative to the laboratory attached to the Earth, light travels faster when it's carried, when it's travelling in the direction of the ether wind, and light travels slower when it's travelling against the ether wind. Just think about walking with or against escalators. Think of concepts of relative velocity from more elementary studies. Now, in the context of working out how much these interference fringes shift when the whole interferometer is rotated, we need to begin by working out a few quantities. So the first quantity I want to work out is T1. And this is going to be the time it takes light to go from P to M1 and back again. You know, if we think of a pair of light beams, and the times they take to travel along here are going to be the same. The times they take to travel along here will be the same. The time differences between this path and this path is going to govern the motion of these fringes. So we need to calculate the time it takes to get from P to M1 and back again. Then we'll do the same thing for P, M2P. So time is distance over speed. And for this part of the arm, the distance is L1. I forgot to label that. The length of the first arm is L1, and the length of the second arm is L2. Time is distance over speed. The distance is L1, and the speed is c minus v. For the return trip from N1 to P, the distance is again L1. The speed is c plus v. Now, when you do the algebra, you'll get this result here. Now, as an exercise, I'm going to ask you to calculate T2. T2 is going to be the time to get from P to M2 and back again. Again, you'll need to do a bit of trigonometry, a bit of Pythagoras' theorem, but you'll get the following when you calculate T2. Now this defines a time difference, which is the difference between time for the light to traverse the first arm of the interferometer and the time it takes light to traverse the second arm. And this time difference, which is here being called delta, is a difference in the times. You can subtract these two things. You can apply the binomial approximation. Remember that V is much, much less than C. So if you have something that looks like, for example, like 1 plus V on C to the power of -2, for example, remember the binomial approximation. This thing can hop down here because V on C is much less than 1 in magnitude to give this kind of thing. So this is an application of the binomial approximation that we met or revised in the last class. So subtract T1 and T2, apply the binomial approximation, and you will get the following expression, equation 27. So 2 on C. Before you write any more, 2 on C is going to be small, right? Speed of light's fast, 2 on C is something small. If these L's are on the order of meters, then you're talking about meters divided by 10 to the power of 8. So these are small quantities. V squared on C cubed, that's going to be small too. So we get this expression. We can stare at it and say, yep, that's good. Now I want to do something, I wouldn't say clever, but I want to do something interesting. I want to rotate the whole interferometer by 90 degrees counterclockwise. So we're going to take the whole Michelson interferometer. This is what this is called. It's an interferometer invented by Michelson. We call it the Michelson interferometer. And we want to rotate the whole thing 90 degrees. And I want to ask the question, what is the new time difference, let's call it delta prime, that you get between the two paths if you rotate 90 degrees counterclockwise? Now there's infinitely many ways to answer this question, but let's reduce it down to two, the hard way and the easy way. The hard way is just to repeat this logic with the interferometer rotated, and when you do that, you'll get 2 on C into L1 minus L2, etc. L1 minus 2L2. This is a cubed. But a more subtle way to work out this new time difference delta prime is to ask the question, stare at this scenario and think symmetry. If I'm rotating this whole interferometer, what changes? How can I stare at this expression here for delta and then stare at the geometry of what's going on here? And then what happens when you rotate the interferometer 90 degrees, leaving the ether wind travelling in the same direction? Can you stare at that and until, and like Sherlock Holmes, see the answer materialise? And just write this down on inspection based on this expression here and the geometry of this thing rotating. This, by the way, reminds me of what's called the Richard Feynman method of solving physics problems, which is that you stare at the problem and then you write down the answer. But having said that, it makes a profound point. On the one hand, it's lazy to not want to brute force calculate delta prime again. This is about seeing elegance and symmetries in your expressions, which help you to calculate things more precisely. And the role of symmetries, and more generally about simplicity in theoretical physics, will come out more and more as this course progresses. Because by the end of the course, we'll be able to say things such as the Maxwell equations are one of the simplest equations that you can write down that obeys the relativity principle. So this idea of simplicity in a very, very profound sense of the term will be, and also symmetry to some extent, will come through in aspects of this course. But as a general rule, the more advanced your studies in physics become, the more important symmetry becomes, and also the more important the quest for profound simplicity based on symmetry becomes. That point becomes particularly evident, by the way, in particle physics courses. All right, I digress. However you want, we've calculated delta prime and delta for the two orientations of the Michelson interferometer. And I claim that the fringes will move as a result of the presence of an ether wind. And what we want to do is to calculate this quantity here called delta in equation 29. And this is going to be the, let me just use a shorthand. It's going to be the number of wavelengths of light. The number of wavelengths of light travelled during the change of time differences. So the number of wavelengths of light travelled during the difference of time differences. Yep. If the time difference changes by this much, that's an extra time that light can travel. And how many fringes will you shift by? Well, it's going to be the number of wavelengths of light travelled during that difference of time differences. That idea takes a bit of getting your head around. If it wasn't clear to you, and it certainly wasn't clear to me when I heard it the first time, think about it for an hour, discuss it with your colleagues until this becomes self-evident. It took me about 2 hours for it to become self-evident, so have a stare at that one. Now, the number of wavelengths of light travelled during the difference of time differences is going to be the same as the distance travelled by light. Yep. During this interval, which is delta minus delta prime. It's going to be the distance travelled divided by the wavelength. So the distance travelled divided by the wavelength. Again, please have a think about that. But the distance travelled by light, distance is going to be speed, c, times time. This may be positive or negative, in which case this will be positive or negative, divided by the wavelength. And we have expressions for delta and delta prime, and when you substitute those in, you'll get the following: v squared, lambda c squared, L1 plus L2. So this is going to be the number of fringes by which this interference pattern shifts. Now let's calculate some numbers. First of all, for Michelson's original experiment and also for the Michelson-Morley better experiment, L1 was equal to L2. And so with this simplification, this formula here becomes 2 times something which is small, V on C all squared, times divided by something which is also small. Now I argued that V on C must be greater than or equal to 10 to the minus 4. Now we want to do what's called the threshold measurement here. Are you going to be able to detect the ether wind or not? What's the minimum velocity that you would expect of the ether wind relative to the Earth? And the minimum V on C you would expect, unless the ether is somehow viscous and dragged along by the Earth, the minimum V on C you'd expect is 10 to the minus 4. This is the order of magnitude for the speed of the Earth relative to the Sun. So you'd expect delta, if we shove a 10 to the minus 4 here, you'd expect delta to be bigger than or equal to that figure at some time of the year. Lambda on L, you can work it out for Michelson's experiment. You'll get lambda on L is 5 to 10 to the minus 7. Here the lambda is here the lambda, by the way, is 6 by 10 to the minus 7. 6 by 10 to the minus 7, and the L is 1.2 metres. So you put these numbers in, and you get that the amount by which the interference fringes shift, at least at some time of the year, should be 4% of one fringe. Now, Michelson was a legend. Michelson-Morley even more so. This was well within the capability of the Michelson-Morley experiment. In fact, it's well within the capability of undergraduate physics experiments. But these are pioneers of optics here, and they could easily measure this fringe shift. So they build this thing. They fully expect, this thing is self-evident, the existence of the ether. They know they can detect it because they've done the calculations. And then what they find is that, and I quote, "there is no displacement of the interference bands." I want to emphasise how pissed off they were, right? You've just done this legendary experiment. You'd win a Nobel Prize if it existed. You're about to detect this undetected matter, and nothing happens. It's actually the most famous and important null result in all physics, in my opinion. They did the experiment again and again, and they never saw any displacement of the interference bands. This is also true even in modern experiments. There's the occasional scare where this null result is stated to be not a null result, but none of those have ever stuck in the sense of scientific consensus. So the point is, we had this null result. So the physicists start dreaming up theories. Why is there this null result? Of course the ether exists. How do we modify the ether theory in order to be consistent with this null result of the Somoli experiment? For example, this person called Lorentz dreamed up this idea of length contraction called Lorentz contraction, which would just compensate for these ether effects. There's lots and lots of forgotten and very, very complex papers which try to explain this null result from the context of a modified ether theory, including the ether is dragged along by the Earth like a viscous fluid, and so it's actually stationary relative to the Earth. All right, so that's it for Somoli. I want to move on now to chapter 3, which is about the foundations of special relativity. So chapter 3, the foundations of special relativity. And the first thing I want to talk about is inertial reference frames. If I was to give you an informal definition, a ridiculously informal definition of a reference frame, I would say it's this. It's an X, Y, Z axis and a watch, right? This is how we describe space and time. Every single click is a point in space, an X, Y, Z, relative to some axis and a particular time. And of course, there's a thing called universal time. Newton said it so, it's self-evident, there's a universal time. And you can put your coordinate axes wherever you want. You can wind your clock forwards or backwards. That's up to you, it's arbitrary. And you describe the simplest thing in physics, the click, the point in space-time, relative to this X, Y, Z, T coordinate system. So we're coordinatizing space-time. So that's a very informal definition of reference frames in general. If I wanted to give a more precise definition of a reference frame, I'd speak of it as a conventional standard of rest, an X, Y, Z axis, which might be orthogonal or not. Could be Cartesian, could be some other crazy system, but a three-dimensional coordinate system, a conventional standard of rest, relative to which measurements can be made and experiments described. After all, we have our X, Y, Z, T, our space-time is like the stage, and we fill it with things. We fill it with matter, we fill it with radiation, such as the light filling this room, we fill it with other things such as sound waves and black holes and X-rays and so on. But that's the stage. You choose your conventional standard of rest. You choose your time, and that's how you coordinatize space-time. It's like a Melway's references or references for positions in space-time. And then all of your objects live in that. I have the position vector r for a point particle. I have an electric field as a function of position and time. These positions and times being relative to this frame of reference. And it's arbitrary, you know. My head is stationary relative to my axes, but my head is moving relative to yours. Fair enough. There's these objects, positions, electric fields, momenta, directions are all going to be relative to a particular frame of reference. There's the word relative again. We could, again, nail an XYZ axis to the surface of the Earth, have a universal time, and measure all positions and all physical objects relative to this. In that case, the sun is moving around the Earth. There's nothing wrong with saying the sun moves around the Earth. It's true, it does, right? If you nail the XYZ T axis to the Earth, then the Earth is the centre of the universe, because the origin of coordinates is precisely here. That's the centre of the universe, and stationary by definition, and the sun moves around the Earth, no problem. the point is that it's motion relative to a given frame of reference. Now I could choose to nail the frame of reference relative to the sun and say the sun is stationary. I could nail it to the stars, some distant star, and call that the absolute, the frame of rest. But the point is it's arbitrary. There's no absolute frame of rest. Yep, there's no absolute frame of rest. If there's no ether, a point I'll get to in a second. If there's an ether, by the way, a stationary ether, for example, filling the whole cosmos, then there is a preferred frame of reference. Nail your XYZ system to the ether, right? And have the whole ether, if it is in fact all moving at the same velocity, choose your coordinate system so that the ether is at rest. A bit more difficult if the ether is turbulent and moving around. Now I want to introduce the frame of reference we're going to use for this whole course, and this is an inertial reference frame. So these are important because the entirety of this course restricts itself to inertial reference frames. Ultimately, we'll state the relativity principle as the statement that every law of physics must be the same in every inertial reference frame. That's the starting point for special relativity. General relativity, by the way, just says bugger inertial reference frames. Why not choose any inertial? Why not choose any frame? Why not choose a frame that does this? You know, the laws of physics should be the same in every reference frame. Is the starting point for general relativity. But we're specialising to special relativity. We're specialising ourselves to an important class of reference frames, the inertial reference frames. So, how do I define an inertial reference frame? It obeys three things. The first is that spatial relations are Euclidean. In other words, Pythagoras' theorem works. X squared plus y squared plus z squared equals distance squared. So the first of three things that need to be satisfied for an inertial reference frame is that spatial relations are Euclidean. Pythagoras' theorem works. The second, if I could use a mathematical symbol, this backwards E means there exists. So there exists a universal time. Of course we can speak of the time. This lecture starts at exactly 5 minutes past the hour, plus or minus 10 seconds. There exists a universal time. Yep. The time at every point in space. And by the way, we can begin to think of a lattice of clocks. So here's a series of infinitesimally small clocks positioned in space in 3 dimensions on some cubic lattice. Yep. So every clock is separated from every adjacent clock by some distance a. And this is in 3D. And all those clocks are ticking in synchrony. That's the universal time. Your wristwatches are all clicking in synchrony with my wristwatch, which is clicking in synchrony with every virtual wristwatch. And these are all massless clocks, not going to gravitate towards each other. In fact, we're going to conveniently ignore gravity for most of this course because it screws up special relativity. So you've got this lattice of clocks ticking away with a universal time. You've got your Euclidean relationship, so you choose any pair of clocks, and x squared plus y squared plus z squared, this is 3D, will give r squared. So Pythagoras' theorem works. And the third thing we're going to need to complete our 3 things that are needed for the definition of an inertial frame is that Newton's first law works. Now, to be more precise, free particles remain at rest or continue to move at constant speed. So free particles remain at rest or continue to move at constant speed. So this is not an accelerated frame. So we can think of this space as being filled with these cubic lattice of massless clocks, all ticking in synchrony, Pythagoras' theorem working. And since each of these clocks are massless, there's no forces acting on them. And since they're all stationary relative to an XYZ coordinate system that is has as its origin one of the clocks, these are all free particles on which no force acts. They're not going to move around. They're just ticking in synchrony. So not a nice picturesque way of visualising this inertial frame. And this is, we're coordinatizing this empty space-time. Ultimately, we want to fill it with particles and fields. Now, this may seem quite harmless, but again, when you look back at this class in the light of some of the things we say in later classes, we'll see some important hidden assumptions that don't work. As one example, is the universal time the same for all inertial frames? When we speak of the time, this lecture starts at 11:05 a.m. We're implicitly thinking of the time as an absolute, something upon which everyone will agree. Are all these universal times the same? Well, Newton would say, yes, they are, except you can just cheat a bit and wind your wrist clock forward a bit. But the point is all these universal times are the same. Is that true in general? Is it true for different inertial frames? If it's not true, what do? Is it true for non-inertial frames? These are all interesting questions. I'm just trying to pick out some hidden assumptions, and the reason I emphasise that is because I've emphasised earlier that we have a very, very finely developed intuition for the fact that the speed of sound is not infinite. We're happy to hear the presence of the jet here, and when we look at it, it looks at somewhere else. We've got good intuition for the non-infinite nature of the speed of sound. We have terrible intuition for the non-infinite nature of the speed of light. But harmless everyday statements such as the time is, which implicitly means the absolute time is actually in violation, is actually implicitly assuming the speed of light is infinite. So there's certain things deeply ingrained in us, even when we speak of the time, the universal time, the absolute universal time, as synonymous with the time, that's actually contradicts the fact that the speed of light is not infinite. And teasing out those hidden assumptions using the process of logic, starting, by the way, with the null result of the Michelson-Morley experiment, and logically constructing a physics, a quantitative physical worldview that is consistent and which respects the fact and which quantifies proper intuition regarding the fact that the speed of light is not infinite, is the business of special relativity. So let's move on to 7, which doesn't exist there, but pretend that item 7 has just materialised at the bottom of the top left board. So here we have Einstein's axioms. And there's 2 of them, Einstein's axioms for special relativity. These actually seem quite harmless, but we'll actually be deriving essentially all of the course with one tiny exception as a logical consequence of these axioms. So this is a very, very clean course in the sense that we look at everything that's gone before, we make some axioms, and then we deduce logical consequences of those axioms. So there's 2 Einstein axioms. I won't write them down, I'll just read them. So the first is the laws of physics are identical in all inertial reference frames. Sounds good, sounds harmless. In fact, it sounds almost conservative. The laws of physics are identical in all inertial frames. Now this actually generalises to all of physics a relativity principle that was well known to Newton and was well known to Galileo. Imagine a ship. This is something that Galileo wrote about, and you're inside this ship and it has no walls. You can't see outside. Modern day equivalent is a very, very good train, a Swedish train or a Japanese train, not an Australian train. So you're in a Japanese train or a Swedish train. The windows are closed. It's travelling in a dead straight line at a very, very uniform velocity. You can play billiards. You can muck around with your springs. You can throw pieces of chalk up and down, and you won't be able to detect any effects of mechanics due to the fact that that train is moving at some uniform velocity relative to the Earth, and I'm treating the Earth as approximately inertial. So the point is the laws of physics, the laws of mechanics, are the same inside this box, this moving box, or for Galileo, a very, very smoothly moving ship. You can't tell when you muck around with mechanics. The laws of physics are the same in any inertial frame. The laws of mechanics, are the same in any frame. Galileo knew that, Newton knew that. All Einstein is doing is say, what's so special about mechanics? Not just Galileo's dictum that the laws of mechanics are the same in all frames. And by the way, Newton's equations, F equals ma, or x double dot, doesn't give a stuff about, if you move the whole thing at relative velocity, nothing changes. Instead of saying, as Galileo did, the laws of mechanics are the same in all frames, Einstein axiom number 1 says all of the laws of physics are the same in all inertial reference frames. Fair enough. Again, I emphasise this seems harmless and even conservative in light of a relativity principle which was long known to be obeyed by Newtonian mechanics. Note the subtlety here also. Newtonian mechanics is a relativistic theory, just obeys the wrong relativity principle. Now, I want to change tack for a moment. When we were talking about the ether, it's one thing to say that the laws of mechanics are the same in all inertial frames. What about the laws of radiation? What about the laws of light? What about the laws of optics? The existence of an ether is actually inconsistent with the idea of the laws of physics being the same in every frame. Let's talk about optics. Light rays. Is the speed of light the same in every frame? Well, if the ether theory is true, it's not, right? If you change from one frame, if the ether is at rest, the speed of light is c. But if the ether is moving this way, at speed v, then the speed of light in that direction will be c plus v. So, if the ether exists, then optics does not obey a relativity principle. The laws of optics, the laws of light rays are different in different inertial frames, if an ether exists. But Einstein looks at the null result of the Michelson-Morley experiment and says, fair enough, there is no ether, get over it, doesn't exist. All laws of physics, including those of optics, are the same in every inertial frame. Yep. So what it's doing here is elevating the null result of the Michelson-Morley experiment to the status of an axiom. It's uncovering a new principle of nature, not just the laws of mechanics, the same in all inertial frames, but also the laws of optics, in particular classical optics, visible light optics. But again, I want to emphasise the existence of an absolute frame of reference with respect to the ether violates Einstein's first axiom. All right, Einstein axiom number 2. So second axiom, there exists an inertial frame, one inertial frame, in which light signals in vacuum travel in straight lines at constant speed c in all directions independently of the motion of the source. So we don't need this ether lake anymore on the top middle panel. The speed of light in one inertial frame, or there exists an inertial frame more precisely, at which light travels at speed c in every direction independent of the motion of the source. But since the laws of physics are the same in all inertial frames, you put these two axioms together and you get what's called Einstein's law of light propagation. Which in a sense defines the ether out of existence. If light travels at speed c in every direction, independent of the motion of the source in one inertial frame, and if the laws of physics are the same in all inertial frames, then light must travel at speed c in all directions, independently of the motion of the source in all inertial frames. Now, when first meeting these axioms and these Einstein axioms, two of them, and their associated law of light propagation, it can be easy to try and I invite you to challenge these things and say, that can't be true, here's why it can't be true, and try to argue logically with your colleagues about, and also with me, as to flaws in this argument. So ask yourself, how can you shoot it down? This is the way knowledge progresses in the sciences. Someone throws up an idea, your colleagues shoot it down and say, here's why it's wrong, here's a better way of doing it. And through that process, it's the ideas that stick, the ideas that can't be shot down through that process of interrogation, of intellectual interrogation, those are the ones that stick. I invite you to take these statements here and argue about them and try to find flaws in them. That's it for today. Thank you.